Hey guys, Miss McCorn here. Today we are looking at a little bit more of Unit 7, Equilibrium. We're looking at 7.8 to 7.10. We are representing equilibrium with particulate diagrams, so you will see a few diagrams in here. Also, we're introducing Chateliers Principle and how it relates to the reaction quotient. So let's get prepared for that by getting out your notebook and writing down these learning targets. So what you see here is that they are giving us the equilibrium constant here, the K. And so the question here is the chemist is testing it. They're giving you the concentrations at a particular point in this reaction. And they're asking, is the system at equilibrium? If not, what direction will it proceed? So this is a little bit of a review. We want to find out, does Q equal K? So we would write an equilibrium expression, and we know to do that we do products over reactants. And then we're going to solve for Q. And we want to find out, does Q equal K? And if Q does equal K, then we're good, we're at equilibrium. But if not, we're going to find out what direction does it need to go in. Okay, and so in this particular case, when we fill in all these numbers, we find out that Q is much greater than K. Because Q is so much greater than K, that means the reaction or the system has way too many products, so this is going to continue to proceed back toward the left, toward the reactants, until equilibrium is established. Once equilibrium is established, of course, then it's going to go back and forth at the same rate. But at this point, the rate of the reverse reaction is going to be much faster than the rate of the forward reaction until the system reaches equilibrium. And that is going to be when the Q is equal to the K. That is when the rate of the forward and the rate of the reverse are going to be equal. So this is just another way to show that reaction, again, is going to proceed to the reactants until the SOCl2 decreases, until the SO2 and Cl2 increase enough and the product there decreases enough so that the system reaches equilibrium. Okay, so this is just a reminder. You might want to jot this down if you haven't yet, but I'm not going to read this whole slide to you. That's just going to waste your time and my time and the video time. So we've seen this before. Go ahead and pause and jot this down. We want to introduce Chateliers Principle today. There are going to be only 3 things that are going to stress the system enough to shift equilibrium so that they can reduce that stress. That's pressure, concentration, and temperature. There we go. All right, so if pressure increases, then the Q is going to change and it's going to go toward the side with fewer moles of gas. Maybe the reactants, it may be the products, but whichever it is, it's going to be toward the side with the fewer moles of gas so that it can reduce the stress, reduce the pressure in order to go back to equilibrium. This is not going to change the equilibrium constant. So the concentration of each of the reactants and the products, so when you see like the concentrations of things, those would change. But what's not going to change is your K. Okay, so it's not going to change the K. We will do examples on this in class. And here is just a particulate diagram. Remember, one of our learning targets is to represent equilibrium with particulate diagrams, and this is a way to do that. So when we look at this, we are going to notice that we have 2 NH3s, 5 N2s, and 7 H2s. And as the pressure increases here, what we're going to try to do is move toward the product side. And we're moving toward the product side because we have 4 moles on this side, and we only have 2 moles on this side. So if the pressure increases here, we're going to move over toward this side so that we can go toward the part where we have less molecules or less moles, so that that is going to relieve some of the stress that the pressure is putting onto the system. Okay, similarly, if the pressure on a system at equilibrium is decreased, again, the Q is going to change. Q is our quotient. Q is the one that changes pretty frequently based on the reaction. Okay, the Q is going to change, and it's going to proceed toward the side with more moles because, again, we're trying to reduce the stress. So if the pressure decreases, it's going to go toward the side with more moles until equilibrium is reestablished. Again, the equilibrium constant is not going to change in this particular case. Here we have another particulate representation of what that would look like. We are going to go, when the pressure is decreased, you're going to go toward the side where there are more molecules. Concentration can be increased, and it works in the same way. Whatever is going to happen is going to try to reduce the concentration in this particular instance. So they're trying to, it sounds kind of like a human characteristics, but it's kind of trying to counteract whatever stress is put on the system. So in chemistry, what's going to happen with equilibrium or reversible reactions is whatever happens to that reaction, whatever stress that you put on it, that reaction is going to counteract it. So if you increase the concentration of one of the species in that reactant or product, the reaction is going to proceed in the direction that's going to reduce the concentration of that particular species. So if you add a reactant, it's going to go toward the products in order to reduce the reactant because it wants to use it up. Okay, so again, it will not change the K. This will not change the K. Changing the concentration is not going to change the K. All right, so again, here we have at equilibrium, this should be a 2, I apologize for that. That should be a 2 moles of NH3, 1 of N2, and 3 of H2. That's at equilibrium. Okay, if we add a lot of NH3, it's no longer at equilibrium, so it's going to proceed back towards the reaction, back toward the reactants, because it's going to try to use up that NH3 until it gets back to equilibrium. And equilibrium is where it has a balance of the moles of that balanced chemical equation there. Same thing, if the concentration of one of the species decreases, it's going to proceed in the direction that will increase the concentration of that species. Does not change the K. I feel like this is pretty self-explanatory. Here we have 11 moles of NH3, 4 moles of N2, 12 moles of H2. If we remove 7 moles of NH3, then we're kind of like out of balance. So if we're out of balance here, then what they're going to try to do, this particular reaction here is going to try to go what was removed. It's going to try to go back to that NH3. So it's going to go towards the product in order to get back to equilibrium. Dilution, it's the same thing as decrease in concentration of something. So same thing with that particular diagram there. Now, stress from changing temperature. This is the only stress that actually changes the equilibrium constant. That is because when you cool something off or you heat something up, you're changing the kinetic energy, and then you can actually change the concentration of things. So you can actually change the concentration of your N2H2, and the way they react can change the concentrations. So when you take heat away from something, you're actually going to shift the equilibrium in the direction that produces heat. So if you remove heat, you're going to go towards the heat. If you add heat, you're going to go away from the heat. And you look at those arrows, it's pretty self-explanatory. It can get a little bit confusing, but we are going to do a lab that's going to help us with this. So we will do some of these examples in class as well. So one of the things I wanted to talk to you, so this particular reaction, the forward reaction is exothermic. It is giving off heat in this particular reaction. So if we add heat, if we take away heat, it's going to go in the direction that produces heat. So it's going to go forward. If we add heat, it's going to try to cool itself off. So it's going to go in the direction that absorbs heat. So if you think about it a little bit more scientifically, adding heat causes an increase in the rate of the endothermic reaction. So heat is required. So it's like giving it more energy. We're effectively adding energy required to make the endothermic reaction happen more often. That extra energy ends up being stored as potential energy. So in that case, that's the reactance that we're having. So why does the KEQ change? Adding heat to the system increases the concentrations, like I was saying just a few minutes ago. Removing heat is going to favor the production of the compounds that possess less energy in their bonds. So this one can be a little bit confusing, but again, we're going to do a lab that's going to help clear all this up. So I hope this helps you understand a little bit more about equilibrium and Le Chateliers principle, and I will see you guys in the morning to do some practice problems. Have a good night.